So this would be Spreadsheet Lesson 8, in which we continue to explore the classic engineering problem, creating a container with a specific limited surface area. It's got only so much material you can make the container out of. This container has an open top, and we had investigated the general geometry of it through this guy right here. What we saw was that in this case, if we're doing an open top cylinder, we have the area is calculated by pi r squared plus 2 pi rh. So area is equal to pi r squared plus 2 pi r. The reason it's not 2 pi r squared is because we only have one of these circles. Pi r squared, we just have the bottom, we don't have the top. And our approach, as you will recall, was to make a guess at a radius using that fixed area, surface area available, and then calculate the height that would create a container, an open-topped cylinder, of that radius and area. And we use this equation here, which we had mathematically manipulated from the available equations there. What we're going to do next is very straightforward. We're going to calculate the volume for each of those options of the cylinder by multiplying pi times the radius squared times the height. So I think I can remember pi r squared h as I move over here, so I'm not going to copy and paste that one. So over here, this equation will be equal to pi times, as you remember, pi is pi open parentheses, close parentheses. And that open parentheses, close parentheses is a way of telling the spreadsheet that this is not the word pi, but rather a function that is built into the spreadsheet program. If you leave out those parentheses, this does not work. So we're going to take pi times r, which will be in that cell there, square it, and then multiply the result of that by the associated height. Now, we don't need any dollar signs in this because we're only going to be dragging it straight up and down. If we're dragging it left and right, then yes, of course, we would need to put in dollar signs to always be looking in column C for radius and column D for height. But in this case, since we're only going to be moving it up and down, it's not going to attempt to change the column references. It will change the row references, but that's what we want. We want a different radius and different height for each calculation. So that's good there. It says the autofill. I'm actually going to accept it this time because this is the correct autofill. I'll show you if I go down here and double check this. This says it's pi times that r squared times that h. So that's really, really good. So what we see is a whole bunch of interesting things. As the radius gets larger, this goes from being a tiny little circle up to something, bigger than a dinner plate. The height has to get shorter and shorter because of the limited area, limited amount of material. But if we look at the volume, it does not do that. In fact, what happens is it increases for a while and then decreases. So for these guesses right here, this value right here is actually the maximum volume. But I want you to think about that for a minute. Does that mean that a radius of 6 and a height of 5.59436, whatever this is here, and you know what I really ought to do, let's just be, well, let's leave all the decimals. Why not? Let's just leave the decimals for now. But I was going to reduce the decimals too. That's kind of ridiculous. But anyway, does this tell us that this is actually the very maximum volume you could get? Well, the answer to that is no. What it tells us is somewhere between the value of radius of 5 and radius of 7, somewhere in that range, this volume increases from 613 up to at least 632 and then drops back down to 595. The actual maximum might lie just before it gets to 6 or just after it gets to 6. We really don't know where the peak of this occurs. Now, we could graph it, and there are some other techniques we could use, but the way I've had you craft this spreadsheet actually makes kind of zooming in on that range from 5 to 7 a little bit easier. For instance, we know it's definitely not going to be hitting a maximum below 5. So we could come up here to our parameter, our starting point for making guesses, and change that to 5. And all it's going to do basically is take all of this information here and shift it up and give us calculations past 10. Now, of course, we've already determined that all of these down here are, ridiculous. But that's okay, because we also know that we really don't have to go past 7 to get this maximum volume in there. It's somewhere between 613, 632, 595, somewhere between 5 and 7. So what we can do is we can make the steps, the gap between each guess here, smaller. Let's try for now 0.2 and see what that does. That gets from 5 to 6.8, and we see as increases, and then drops again. So now we're seeing that 5.8 is actually closer to the ideal radius for maximizing this volume with this limited surface area. So this setup here, where we have a starting value and a stepping value, and you're going to see me use this a lot as we do some other analysis, starting in value and stepping value as we're making some guesses over a range, will allow us to change where we begin our guesses and how far apart the guesses are. And by doing that, we can kind of zoom in on the ideal value, which in this case is right there. But you know what? This also would also make this be quicker, smoother, faster, would be to try to identify that maximum volume in this column without having to actually look at the numbers. And there is a way to do that. So what we're going to do now is we're going to type the word max V here, and just under, or you can max vol if you want to do that, something like that. Anyway, and underneath it, there is a function built into the spreadsheet, and it's called max. And what it does is it gives you the maximum value in a range or data set. So what we're going to do is we're going to do max, and we're going to open a parentheses, and then we're going to click and drag over all of this range here. Oops, I didn't do it quite right. Let me try and click and drag over all of this range of values here. And then we'll close parentheses. And what this formula does that we've written here is it scans E4 to E13, looking for which of those numbers is the largest in that range. And then it will display that result, which happens to be 633.18. It gives you a preview there of what it's going to say in this spot. So if I do this, there's that max. If we went back to, notice that's 633. If we went back to 1 as our starting point and 2 as our steps, we only get to 632 there. So by going in those steps of 0.2, we can get an even finer idea of what is the maximum possible volume of an open top cylinder with an area of 324. So that's kind of cool, but all it really is doing is tell us what number to look for in this column. But that sounds interesting to me. What number to highlight, kind of, in a range? This sounds like a perfect case for conditional formatting. So we're going to apply conditional formatting to help us find that number without having to look at the actual numbers. So we're going to highlight this range. We're going to go to Format, Conditional Formatting. I'm going to say Apply to that range if the cell, in this case, is going to do is equal to, and then we're going to say E2. Let me put the dollar signs in there, $E, $2. So it's going to highlight the cell that's equal to E2, and just so it jumps right out at me, I'm going to make that background bright orange. That looks good. I mean, you can do whatever color you want, doesn't really matter. Click Done, close this up here, and so now what we have is, there's my maximum. If I went back to starting at 1 and increasing by 1, then it jumps 6. There's your maximum value there, 6 and 5.59. If we zoom in a little closer, starting at 5 and going by 0.2s, we now find that it's 5.8. But actually, we don't know that this is the best. It could be anywhere between 5.6 and 6, really. So again, we can use this start and step to first, don't look anywhere further lower than 5.6. So let's change our starting value to 5.6. We're just kind of homing in on an answer now. And then let's make our steps be 0.1. Now we see that rather than 5.8 being the ideal that was in the last calculation we did, 5.9 is actually slightly better. Now at this point, the better is not by a lot. 633.11, 633.19. We're really talking about at 100th of a cubic centimeter here, or cubic inch here. But it's going to be, let's say, enlightening for us to investigate even further. So what we can do is we know now that the peak is somewhere between 5.8 and 6. So let's change our starting value here to 5.8. And now make our steps even smaller. Let's go by 0.02. And now we see 5.86 is better than 5.8 or 5.9 or whatever it was last time. Now something interesting begins to become apparent. Compare these two numbers. What do we notice here? 5.86, 5.869. Maybe the ideal dimensions of an open top cylinder or the maximum volume dimensions of an open topped cylinder of limited area, limited to 324, or any really, is when the radius and height are equal to each other. Let's go ahead and just continue to zoom in on this to see, but that's an interesting thing to suggest. We won't want to start at 5.86 because it might be somewhere between 5.84 and 5.86. 5.84 and make our step a little tiny bit smaller. And we're seeing 5.86, 5.86 again here. Okay, so let's change this to 5.85, the one just prior to where my peak is. I make this step even smaller. And now we see 5.864, 5.861. All right, well, let's change 5.862 is what we want to put up here. 62. And change this to 0.001. Now, of course, at this point, we're getting a little silly. We're looking at thousandths of an inch on our radius. But, again, 5.863, 5.863. It really is looking like we're zooming in on a place where these two values are equal. You can see I get even smaller. I get that. Change this to 5.863 here. It pulls up. Change this to way out there. You have 5.8632, 5.8632. So it really does look like what we've discovered is an interesting phenomenon where the radius and height are equal. Now beware, what we're talking about here is something that's shaped more like a tuna can than it is like a soup can. And that leads to a really interesting engineering question about why would, engineering-wise, the tuna can be the one that makes the most sense here, and yet most things that we buy in cans aren't made like this. So go back to our problem definition and give that some thought. Anyway, the next question we'll investigate is whether or not a cone, like an ice cream cone, might actually hold more, might actually be a more efficient shape for containing materials if your top is open.